The visible universe, galaxies, stars, nebulae, is only a part of history. Most matter does not emit light and cannot be directly observed, but its gravity organizes the cosmos on a large scale. That dark matter acts as the skeleton upon which galaxies and clusters form, determining what structures are born, how they grow, and how they are distributed over time. Before going into this fascinating topic, we invite you to subscribe to our channel and give like to this video. Your support is fundamental to continue creating interesting content about the universe and cosmology. To understand the invisible architecture of the cosmos, cosmologists use a mathematical tool known as halo mass function. It describes how many halos of dark matter exist according to their size and at what point in cosmic history. A new scientific work proposes a theoretical reformulation of this tool and contrasts it with ambitious simulations. Dark matter halos are mass concentrations involving individual galaxies or large clusters. Although they cannot be seen, their gravitational influence is measurable. Knowing how many exist and how they are distributed is essential to test the current cosmological model, which describes a universe dominated by dark matter and energy. Since the 1970s, different models have tried to predict the abundance of these halos. Press-schechter's formalism was the starting point, but the authors of the new study recognize that no current model provides a self-consisting description of the MFH throughout the entire cosmic history. The new model, called GPS+, introduces a key modification in the criterion of gravitational collapse. This theoretical framework accurately predicts the abundance of dark matter halos in a wide range of masses and displacements to red, without explicitly depending on time. One of the central characteristics of the GPS+ model is that it is based mainly on the variance of the linear density field. This means that the temporal evolution is introduced naturally through the physics of the growth of structures, without the need for adjustments for each epoch. To check the model, the team compared it with the UCHU simulation suite, which allows measuring the mass function in an extraordinarily wide range. Quantitative comparison is the core of the study and shows that GPS+ matches the simulations within 10 to 20%. Another crucial aspect is the definition of mass used for halos. The work shows that using the definition M200m leads to an almost universal function, while using the traditional virial mass introduces notable discrepancies. This has practical implications for the great cartographed sky today. The relevance of the model is not limited to mathematical calculation. A more precise mass function allows better translation of observations of galaxies and clusters into information about the fundamental physics of the universe. This makes a difference from other approaches more dependent on empirical adjustments. Overall, the work led by the Instituto de Astrofísica de Andalucía expands the range in which it is possible to consistently describe the invisible structure of the cosmos. It is a technical refinement that provides a more reliable mathematical map to explore 13.8 billion years of cosmic history.